yes, usually you have a molecular cloud in our galaxy. This picture is showing you one. It doesn't come up tremendously focused, but anyway. We have a cloud of gas and dust that starts collapsing, and then any blob that collapses there is initially rotating a tiny bit. So when you collapse it by about 1 million times, it will rotate quite fast. So at the end, you never form a star like the Sun just by itself. You form it surrounded by a disk, which is also very nice because at the end you form planets from that disk. And this is also how we know nowadays that about every star has planets around. So the problem with these things is that we are normally interested in knowing how a planet like the Earth is forming, and a planet like the Earth is forming very, very close to the star. So it's in a place that is tiny and is very, very hard to see. So then what can we do with that? So this is the leading point here. And this is also work that I'm doing with a lot of collaborators. I have collaborators in Germany, France, in China, and Italy. And also I wanted to give a special mention to Dundee and Chris Templeman, who are students from the University of Dundee. So first I'm going to show you a bit of a small movie. It's an artist's impression of what a young star with a disk looks like, so that you kind of get what I'm going to talk about. So we have here a star is born surrounded by a disk. The disk is actually from time to time accreting onto the star. When the disk accretes onto the star gets brighter, as you can see. And then well, in this movie you can also see that the dust in the disk is actually melting. And then when it cools down again, it forms crystals. And these crystals may be also blown away. When the stars are accreting, they also get like a very strong wind. And they land in the places where we form comets, right? So this kind of behavior is usually happening in timescales comparable to the rotation timescale of the disk. So if we add about the distance of the Earth, it's going to be 1 year, right? So it doesn't need to be that long. But this was an artist's impression of an event that happened actually in 2008 when we were following this object. But how do we get to know all that? And the main problem with that is what I'm going to show you now. Okay, so I mentioned initially, you have a cloud of gas and dust in our galaxy that gets very cold, and it's all a fight between the pressure of the gas and the gravity. If it gets cold, the pressure of the gas goes down and things start collapsing. But what we get initially is what we call a protostar with an envelope. So this kind of blob of collapsing cloud is called the envelope of the protostar. And if we had to see one in a nearby star-forming region, like the Taurus star-forming region, it will be the size of about 2 to 8% of the diameter of the full moon, right? The entire envelope. Inside this envelope, which has a size of a couple of light months, we form our star with a disk. This disk is a protoplanetary disk, and initially it's usually a few times the size of the solar system. So the entire blob here is about a few percent of the diameter of the moon. And now I'm going to zoom into the disk. So this is another kind of cartoon of these young stars. The young stars, like the Sun, when they are very young, they are called T Tauri stars because the first one that was identified was T Tauri. So now this is, the previous one was kind of to scale. This one is harder because, for instance, for you to be able to put a dot in PowerPoint, I had to put it 100 times bigger than what it would be the real star, right? And we have the disk that is kind of flat, although it's also a bit flared because the gas is pushing it out. And that's about a few times the size of the solar system, which means that the Earth will be forming in about here. Jupiter will be forming about here. Pluto would be about there, right? And remember, that was a tiny disk that was in something that was about 2% the size of the moon, right? So in general, if we want to see that, it's like you put a couple of centimeter marble on the moon and you try to observe what happens, okay? So we have nowadays big telescopes. So the biggest telescope that we have is the ALMA interferometer that you may have heard about. Is in Chile. So an interferometer has advantage that it works resolving as if it was a telescope, as big as a separation between the antennas, right? So if you put antennas apart, this kind of can resolve as if you had a couple of kilometer big telescope. So that's the biggest resolution we can have. We can think about building telescopes that are 10, 30 meters, now a bigger telescope coming by. But if you want something even bigger, and you really want to get something bigger, if you want to study the tiny details, you need to have an interferometer. So that's the ALMA interferometer in Chile. And if you use it for a region, nearby region like in Taurus, you see that actually the maximum you can resolve is about the distance of Jupiter. So anything happening closer in, like a newly forming Earth, is going to be too tiny. And if we really want to study how the star is forming, that's going to be totally tiny. So most of the interesting scales that we want to look at, they are very tiny. And they're not only tiny, they're also very faint because they are very small. So the emission that you get depends on the area of your object. So if the object is large, you see a lot. If the object is tiny, you don't see much. And just to show you a bit, I'm going to show you one of the most famous pictures from the ALMA telescope that you may have seen. So this is an object that is called HL Tau. It's a young object like the sun surrounded by a disk. And this image is very, very impressive because you see the disk, you don't really see the star because this is a radio image and the stars are much hotter to don't emit so much in radio. But all these holes that you see here, all these gaps are formed by planets that are forming in the disk. So all these holes that we see here, they are created by planets. So we can actually see there are planets forming in this disk. But if we go back, we want to understand the solar system and the Earth. If we compare it, this is actually the solar system there, right? But actually, these are the orbits of the gas giants and the ice giants, right? What we have, the Earth is again in something super tiny here. So if we compare that with this image, the Earth will be in the central blob where we don't see any detail. So did you get the problem here, right? So even if we use the best telescope we have for getting an image, we don't get an image that is good enough to see how a planet like Earth is forming or how the young star is evolving. So then the question is, how can we get an image, or how can we understand or get information about something that is too small to be resolved with telescopes? And even if we had kilometer-sized telescope like an interferometer, even that is not enough. So then we actually have two things that we can use. And they may sound a bit strange, but one of them is color, or wavelength, and the other one is time. So this that I'm showing you here is, we are going to first see what we mean by color and what the color can tell us if you look at a star with, let's say, different color filters. So when I'm talking about different color filters, I'm not talking about just the visual colors, you know, like red or green or blue. I'm just talking about the full electromagnetic spectrum. So we have things ranging from X-rays down to ultraviolet, and we have optical visible light. Then we go to the infrared, to the far infrared, to the submillimeter and radio waves, right? So in general, the way objects emit depends on their temperature. Something that is very hot is going to be emitting kind of shorter wavelengths or more energetic light. Something that is very cold, we know that, like we get, if we have welding, we are welding something, it initially gets red, then it tends to get white when it gets hotter, then it tends to get blue, then when it's melting and running away, anyway. So in a star with disk is something similar. So we have the star, right, in the center. And this is not to scale in this case, okay? So we have the star surrounded by a disk. The star is giving its own light, but the disk doesn't. So the disk is just being warmed up by the star, right? So then this means that the parts that are very close to the star, they're going to be very hot, and the parts that are very far from the star, they're going to be very cold. So this means star, usually with the temperature of the star, is going to be emitting light that is mostly at visible wavelengths, like the sun. Because these young stars are accreting, that is matter falling in, wherever the matter hits the star, it creates a hot spot. They are a bit like hot spots in the sun, but they are much bigger and hotter. So then they are going to be emitting things like ultraviolet. Very close in the disk, it will be so hot that the material that we have normally in the disk, which is dust like sand, is usually like silicates, it's really like sand and gas. So all these silicates, they are going to sublimate, they're going to turn into gas, and they won't be there. Actually, even the molecular gas, they will have a molecular hydrogen, for instance, that will be so hot that it will also split. So what we are going to have is atomic gas, so just the atoms. Then when it gets a bit colder, we can start having molecules of gas, mostly hydrogen. When we move a bit further, it gets cold enough that the dust can condensate, like you saw in the first artist impression. Also, when the star gets very hot, the dust is melting. So if we are far away, the dust is in dust form. And then it's going to be still very hot, so it's going to be emitting in the infrared. If we move farther out, it's going to be colder and colder and colder, and then it will be emitting longer wavelength light, like far infrared or down to radio. So if we go back to where what ALMA can tell us. ALMA is a radio interferometer, so it can tell us mostly about radio emission, and it can only resolve something that is about the distance of Jupiter. But just to remind you a bit, what we are interested in is what is happening here. Now, the important point is that even if our telescope is not strong enough to create an image where we see different parts, we know that if we are looking at this in optical light, the light is going to come from the star. If we are looking at the ultraviolet, this is going to come from the hot spots on top of the star. If we are looking at the infrared, this is going to be coming from the region where Earth-like planets are forming. And we can also try to detect the gas that we have here, the atomic gas or the molecular gas, and then this is all going to tell us information about different places. So because I know that this is a kind of a complicated concept, and this figure is complicated as well, what I'm going to do now is I'm going to bring you through a trip through a star-forming region, which I have been working on this one for a very long time since I was doing my PhD, so I keep looking at this region. It's in the Cepheus constellation. So you can see Cepheus here, this region is here. It's called IC 1396A. And actually, if you have a not so small telescope, it's quite nice because it has a lot of clouds. And it produces a nice picture, actually. I see there is something strange with my letters. Some of them look small, but that's something funny with the projector because here they look big. Okay. Anyway, so what I'm going to go now is I'm going to show you some images of one of these globules or star-forming regions in IC 1396 through the eyes of different telescopes. Okay, so this is first an optical telescope. I have here like the electromagnetic spectrum, the kind of light. So we have here in the visible range. And I'm actually going to move to longer wavelengths because, for instance, the X-ray images they don't look very nice. Anyway, so this is, if we look at the object with an optical telescope, this is what it looks like. This image is taken with a 3.5-meter telescope in Calar Alto. And then what we see here is a lot of stars. Then we see this cloud where stars are forming. And well, we see the cloud mostly because we don't see the stars. We don't see the stars that are in the back, right? So most of the stars that we have here in the field that don't belong to the cluster that is being born. But we have this cloud here that covers the background stars. This cloud has a small hole. So this has been blown up by the young star that is forming in the center, right? And then it also has this shape here because there is a very massive star that is about here, right? It's not in the picture, but it's kind of carving this globule. And we also think it's inducing, it's pressing it down so it start forming more objects. So what we see here in optical light is something that is hot, like a star. So I have here our thermometer will be about 5,000 degrees. So if you look at the stars, they look all like dots, but what we are seeing here is really the emission from something that is very hot, like the star. And things that are colder, like the cloud, they just appear as opaque. You don't see anything. Now this image is also in the optical, but it's what is called an arrow band image. So it's also a bit redder. So if we want to talk about temperature, the temperature of the things that we are seeing here is a bit colder. It's about 4,000. This is taken with the 2-meter telescope in Colorado in Spain, and with an instrument that is called a Fabry-Perot interferometer, which is like 2 plates of glass that you can tune to get a very narrow band filter. Mm-hmm. And this is what we have done here. So the green color is a false color, but is picking up a line of sulfur, which we know that gets activated in the places where stars are interacting with the cloud. So then, for instance, the rim of this globule is very bright in green because we have the massive star here that is blasting it away. The rim of the small hole there is also very green because we have the little star there. It's also blasting its own hole away. And we see this kind of funny wiggles, which is, these are jets from the young objects that are in there. We don't see them, but we see them that they have wings that are trying to carve their way out of the cloud as well. So now I'm going to move even farther down. This is the infrared. And what you can see, well, the globule still kind of looks the same, but suddenly it got transparent. So the optical light can't get through the dust of the molecular cloud, but the infrared light can. And now suddenly we see a lot of structure and a lot of other objects that were not visible before. These are mostly the young objects that are being formed in the cloud. The other important thing is that now the temperature of these objects that we are seeing went down. So even though we still have dots that look like dots, that look like stars, what we are seeing here is not the emission from the stars, it's actually the emission from the disks that are surrounding the stars. And actually, from the temperature here will be like the region where Earth-like planets are forming. So we have an issue that telescopes are not good enough to resolve the small-scale structure, but the light that we are getting from these dots, even though it's not a picture of the disk, is coming from the disk and can tell us information from the disk. Actually, this is taken from the Spitzer Space Telescope, combining several images. Spitzer was a very small telescope, was 70 centimeters only, but it was really powerful to work in the infrared. And we had to send telescopes in the, if we want to observe in the infrared, we actually have to go out of the Earth, because this is the temperature of the Earth. If you put them in the Earth, what you're going to see is a nice glowing atmosphere, right? So you are not going to see anything. The sky in the infrared from the Earth looks like all shiny day or night. It's just the temperature we have. So I keep going to longer wavelengths, and my thermometer is also going down, right? So now we went, this is also from the Spitzer Space Telescope, but it's a longer wavelength, it's 24 microns. And you have seen now the image changed quite a lot. I don't know if you know this, but we have now a lot less dots or stars than we had before. And the cloud is getting shinier and shinier. This is because we are reaching the temperature of the cloud itself. And then you still see these are dots, right? They still look like dots with a bit of diffraction rings, but they're dots. But again, what we are seeing here is not the light from the star, it's a light from the disk that surrounds the star, and all the stars that didn't have any disks, they're gone. You don't see them anymore. And you can see also there are some pretty bright things that are coming up here. These are like called the sort of protostars, or like this one here, that before we couldn't see them at all. Oops. Now, going to longer wavelengths. So this is the Herschel Space Telescope, which is working at 70 microns. So this is what we call far infrared. And now we are tracking things that are much colder. So it's very hard to see from the contrast, but you still see some of the objects that have disks. They are about here. But now the cloud is getting really shiny. And now something here appeared that we didn't see before. And actually, when I got this image, that was from my own program from the Herschel Space Telescope. And when I got this image and I saw this rim and there is a star here, I was thinking, how did I miss this in the Spitzer telescope? And I went there, I can't have missed such a big thing. And actually, you don't see it at all with the speed side because it's so cold that you really need to go to very long wavelengths, otherwise you don't see anything. You can also see other structures in the cloud, right? Now, going still with the Herschel telescope, but this is 160 microns, so this is even colder. We can see here some round structure. This is a protostar, like the one that I was showing you the cartoon initially, with a big envelope. And inside is forming a young star with a disk. And then we also believe that this one has formed right there because of the pressure of the massive star that is pushing the gas here and making it collapse. And then I have a final image to go through this cloud here. So this is taken with the IRAM radio telescope, which is also in southern Spain. So this is a radio image, and then radio you can again do from the Earth because the atmosphere is transparent. But I have a bit of the contour of the cloud because you would not be able to distinguish the cloud anymore in here. The only thing that we see at this radio image, super cold temperatures, is a very cold protostar with a bit of the high density material that is surrounding it. Okay, so this is one of the ways that we can get information, even though in every picture the protostar or the disk is just a dot. The information that the light of different colors is bringing us is telling us about different regions if this, in this system, in the star or in the disk. So we can actually learn a lot about that. And now we can think, what about if instead of just using these kind of filters, which are kind of broad, we were splitting the light as finely as we could? Like if we had really a ton of colors. So this is what we do with spectroscopy. And this is what I call also reading between the lines. Because what I do, and actually I work mostly nowadays with spectra, what I do is to look at a lot of spectral lines. And what you can see there is what happens if you split the light of one of these young stars. So what you see up there, all these kind of wiggles up and down and back and forth, this is not noise, these are actually emission lines in the spectrum of the star that are coming from this hot spot that the star has there. And you can see there are a lot of lines, which means that all these lines are telling us a lot of information about many things, including what the star is made of, and how it is moving, and what is happening on top of it. So, just going to go briefly about, I'm going to the other end of the size, right? So we have been talking about protostars that are very large, and they have envelopes that are a couple of light months across, and now I'm going to atoms. Because at the end, when we look at spectra, what we are seeing is the atoms that we have in our star. When I was a little kid and then we were learning in school, stars are made of hydrogen and helium, I asked the teacher, okay, how do we know? Right? Because, I mean, it's not like you go to the star, you grab a bit, you bring it to the lab, and you say, okay, that's hydrogen. No? And then actually the teacher didn't know. So then actually one day I crossed with a book that was talking about spectra, and then suddenly it was also clear, right? Yeah. And it was so interesting. I had liked rainbows very much before, and then I realized actually these are rainbows. So they are really super interesting. If you make a rainbow from a star, you can really learn a lot. So you have an atom, right? The atom has orbitals and has electrons that are moving there, and it has like energy levels, right? So you have a photon of light that comes in. If the photon has the right amount of energy, the electron is going to jump up, and then the photon is going to be gone. The same if you have a very hot spot on top of the star that is very, very hot, and this means that all the electrons are up there already. You leave it there, the electron can fall, and when it falls down, it just produces a photon with a very specific light. So then we get a line in our spectrum, right? I made this cartoon for my children, and they really like the electron with feet. So essentially, every atom is like a bit of ladders of energy. So between all these atomic levels, what you have here is like a ladder, and every step has a different amount of energy. So when the electron gets a punch from the right energy, it jumps on the next level, right? And then it just absorbs a bit of the energy. and then when it gets bored and jumps down the hand level, then it will release the photon, and then we see our line is back. No? So it's also a bit like if you have one of these singing balls, no? Is you excite your atom with the right energy, or you excite your ball with the right energy, and then the water is coming in different ways, right? So it's the same with an atom. And actually, if you don't have a singing ball, I tried to make our work in the kitchen sing, and it works. It's not so spectacular, but actually it works. You have one that is a pot that is just a piece of metal. It kind of works. It's also a lot of fun. So, with all this at the end, the spectra are a bit like what I call this, like, this is actually, this picture is what I saw in the book, where I finally, that was from the children book that I finally learned how do we know that what the stars are made of, right? So I thought, well, this looks like a barcode, right? And actually it does, no? So it's like the barcode of a star, and then the same, then you scan a barcode and you know whether that's potatoes or eggs. You scan the barcode and you know what kind of object it is, what kind of atoms it has in there, because different atoms have different levels of energy. They have like different ladders. When the electrons are jumping up and down, you just see different lines, right? So then you can see the spectrum of the sun here has some lines. Spectrum of a colder star has different sets of lines, and spectrum of a hotter star has also different sets of lines. And then also you can even do more interesting things. So in case of the young objects that we saw before, instead of having the lines in absorption, it has the lines in emission, mostly because we have this very hot material that is releasing the electrons down, and we see a lot of lines. But the other thing that you can see here is these lines have some names, right? So Fe, this is iron, H, alpha, that's a hydrogen line, right? Calcium is ionized calcium. So we can tell the temperature of the star, we can tell what kind of atoms we have, whether they are ionized or not, so that also tells us about the density that we have in the star. And the other important thing is that we can even tell whether the star is moving or how it is moving. Because you may have heard about the Doppler shift, and it's also one of the ways that people use for finding planets. So when something is coming to us, the lines are moving to the blue. When something is going away, the lines are moving to the red. Now, this is also why we know the universe is expanding, because the light of the galaxies is redshifted. So we also can see how the lines are moving, and this also tells us how our object is moving. So these are the things that we can observe. Now we can go use our telescope and take images at different colors of wavelengths, or we can take spectra. But actually, how can we get even more information than what just the image or the spectra are giving us? So to answer this question, I'm going to show you a couple of recent missions or telescopes that are ongoing now, right? So we have some big ones like the Vera Rubin Observatory. We have some space ones like Gaia or Kepler or TESS. We have some not so large ones like the Zwicky Transient Facility or the Havalambre Observatory. That one is in Spain, and I got recently 800 hours in that one for the next 5 years. So we have a lot to observe. Or the Las Cumbres Observatory Global Telescope Network that has actually small telescopes all around. And then this symbol that I have here is from a project that they have at the University of Kent, which is actually a citizen science project. And these telescopes, they are not so large, but they all have something, a single thing in common. They are some in space, some on ground, different places, but the main common they have is that they are all using the time dimension to make their measurements. So they are not static things that are just looking at taking pretty pictures, but they are actually looking and looking and looking and looking again. So that's actually what I'm going to do with my 800 hours. I'm going to be looking and looking and looking again for 5 years to several young clusters to see how the stars are changing and try to get information from there. So how does it work? So in general, time and space are related through velocity. When you were in school, that's what you calculate the space that you have been running just by taking the time and the velocity. Or if you sit in a rocket and you start traveling, if you travel for a very short time, you're going to go through a small distance. If you travel for a very long time, you're going to go for a long distance, right? So in general, every spatial scale is related to a time scale. And then the interesting thing is that actually it's easy to take an image of something that is very large, but it's very hard to see it changing because we will need a signal, something that is moving through a very large space, and this is going to take a very long time. But on the other hand, if we are interested in seeing how a very small thing is changing, small like a star, just the surface of a star, or an Earth-like planet that is forming, that's going to be moving much faster. You know, like the star is going to be rotating in a few days' time. The planet, like the Earth, is going to be rotating around the sun in about a year. And depending on what we are looking at, if we have light that is coming from the star and, for instance, heating up the disk or being reflected in the disk, that's going to move distances, like the star essentially in minutes or less is going to be in the planet region in a couple of minutes. It's going to be really super far away. Within a couple of years, it's going to be really very far away. If we are looking at something else, like for instance, the rotation of the star, that's going to take days. No, but it's going to give us information about something that happens at the stellar radius just in a few days. If we are looking at something like a sound wave or a pressure wave propagating through our disk or through our so in the inner part of the planet-forming disk, so our sound waves are going to take a couple of months or years to travel, right? So these are not so long time scales because we're talking here about days, months, few years. So these are, in principle, human time scales. And these are also scales that you can really resolve with an image. And then there is also something even more interesting, which is even if we are thinking about planets like Jupiter, and so that take a longer time, we're thinking about decades, we have nowadays very good spectra from different telescopes since, let's say, the year 2000, so this is 20 years. We have very good photometry since the 70s, so this comes to 50 years of good data. This is a lot of orbits of Jupiter already, right? So, and the data that we have is only getting better and better. And what telescopes do is normally they keep the data in an archive, and the archive becomes public normally after a year. So the person who took the data has about a year to do whatever they want. After a year it becomes public, anyone can do things. So this means that we have, if we look at just the images or the photometry, how it changes, we have 50 years of good data and even longer of not so great data but quite impressive. And if we want to do spectroscopy, we have also 20 years of good data. And we shouldn't really underestimate the time scales for which we have good data, or how long have humans been observing. So what I'm showing you here is a very old movie. And then the dates that you are going to see, you will see 16, 17. This is not 2016, this is 1900. Okay, so this is an object that is called the Hubble's Variable Nebula, right? And you can see here observations for more than a century, right? So the star is variable, and it has this nebula where you see shadows being projected on the nebula. And you can see how it changes, right? And then this movie I have is very long. I only cut here part of it, no, but they have the movie going until the 60s. Essentially. And people have been observing this, right? So we have even more data. So if we want to study how these objects is changing and what is causing the variations, we have more than 100 years of data. And something that people realize is also when I said the rate at which things are changing has to do with how big the things are, no? So in this case, what we have is a nebula, which is pretty large. It's several times the size of a solar system. But then you can see here, we see differences. Things are changing from month to month. Actually, you can see the shadows kind of moving and developing like every year and a half, right? So then we know that it's not something that is happening in the nebula, right? Because the rotation of something that is several times the solar system is going to be several hundreds of years. It's not going to be months. The only thing that can be traveling through the nebula in a couple of months fast enough is light. So what we are seeing here is essentially there are things crossing between the star and the nebula. They are very, very tiny. We can't really see them. But it's like when you put your hand in front of the projector, or if you put a hand in front of the projector, here you see funny things happening, if I can reach the projector properly, right? So it's about the same. So what we are seeing here is the hands that are coming around the star, just projected on the big nebula and changing. So it's not only that we can see the variations on the star, but we can actually amplify them over a big screen and look at them much better. Okay? So you have seen here we have hundreds of years of data, we have more than 100 of years, and then we can actually do quite a lot. But why do we want to look at these objects that are variable? Well, we want that first have fun. You know? Looking at the star that is changing all the time is actually quite a lot of fun. Then these are also, they are changing because they are forming planets. If we want to understand how planets are forming, then we should have a look at them. But also it's a special chance to do an experiment. What I do is astrophysics, and people say, well, physics, you bring something to the lab, you poke it a bit, you see what happens. You can't bring the star to the lab and poke it a bit. The good thing about the young objects is that they are self-poking, right? So they are having disks that are falling on that, they have things that are changing. So they're doing the experiment for you, you just have to observe it. And then you can actually learn quite a lot. So what I'm going to show you here is some of the variable stars that I have been looking at, and a lot of things that you can learn. So this is a list of some of the interesting objects I have been looking at. So X-Loopy is one that actually, the movie that you saw initially of the disk and the crystals was actually made after X-Loopy. This object had a big eruption in the 50s, and then had another big eruption in 2008. And we could actually learn how these crystals were forming the disk. And it keeps also having smaller kind of eruptions from time to time. GWORI is also a very interesting object because actually it's a triple star. So, and it's all with a disk. So two of the stars are inside the disk of the first big one, right? And then if we look at how things are changing with the period of the stars, so one of them has a period of about a year and the other one about 8 years. So again, they're not so large. It's like if we are putting a probe in the disk and moving it around. So it's actually telling us a lot about the structure of the disk. Then Assassin 13dB, that is actually the one that you see here in this picture. So it's the one in the center with the square. And you can see that it changes sometimes from being a very red and faint object to be a bright and blue one. And it's also the one that you saw the spectrum before. When it gets hot, it gets a ton of emission lines because it had a lot of hot spots. And then the ones that I'm going to talk a bit more in detail are these three. So J1604, which is a star with 2 disks. CCMA, which is one star where we see the disk when it gets in outburst. And Armon, which is actually the one of the Hubble Variable Nebula. So thanks to the nebula, we can actually look at the star from 2 directions. So the first one, J1604, which is in the kind of Ophiuchus region. So this is a star that, again, some of my letters are funny. Anyway, so this is a star that was known for having a disk that is very large, and we see it in early phase-on. So it's so large that you can actually see it in the infrared with big telescopes. So the dot that you see inside is not the star, it's actually the coronagraph covering the star, and then you see the disk, right? Nice and bright, only that people realize it has like dents. And people saw it doesn't only have dents, but if you observe it on consecutive nights, it looks like the dents are moving. right? So this is a big disk. It's like the size of the solar system, right? So it can be that it's changing or rotating from night to night because it will take a couple of 100 years. So what we have here, again, something that moves that fast at such a faraway region has to be light. So it has to be shadows cast by something which is much closer to the star than this big disk. So this object actually has not one disk, but has two disks. So it has the big disk that we see kind of face on, and then if you can see the cartoon, it somehow it became very pale. But it has a smaller disk inside, which is nearly 90 degrees, right? So then that disk is producing these two shadows because it's so highly inclined, and then the disk is kind of wobbling, right? So when it wobbles a bit, you see the shadows a bit moving, right? And then, because we are looking at that kind of from the top, then you think, but then we see the disk crossing in our way. And the answer is actually we do. So if you have a look at the brightness of this disk, so what we have here is the flux or the magnitude. And over time, you see, so if we look at the object, we see that tends to have sudden brief dips, right? Sometimes the dips are kind of happening more frequently, but typically happen every 5 days or every 2.5 days. Why? Because we have the disk, the small disk in there, which is falling on the star through two channels. So normally it has one channel that is bigger, and this is the one that produces the big dips. Sometimes there is a lot of mass moving through the disk, and then you get two dips. So the star rotates in about 5 days, so you see every 5 days you see the big channel coming, and if there is enough material you will see the second one coming at 2.5 days. And then the funny thing is that this is also changing quite quickly, so every 10 or 20 days things are looking different. And what we did was to calculate the amount of matter that has to be falling on the star just to produce these kind of dips. And then indeed you see that with the amount of matter that you see in the inner disk, you are essentially eating it up in 10, 20 days and then bringing more from somewhere else in the outer disk. So then the other thing that we did with this object was to look at the spectra. And this is one of the hydrogen lines that you see in high resolution spectra. And the different colors, just different dates. So that's harder to understand, but essentially when you have matter coming in, you see things moving away, so you see an absorption that is moved to the red, which is this one. So when the line is small and thin, it means there is no matter coming in. When the line is big with a dip, it means that there are things falling on the star, right? So if we see here that the amount of things falling on the star is changing in time, and if we compare again the magnitude with the time, we see there are many times when there are dips, but there are also times when there are no dips. And if we looked at the infrared data, that figure is more complicated to understand, but essentially, if we see, there are times that we see infrared emission, which is coming from the inner disk, and there are times when we don't see any infrared emission. So the inner disk is gone. And then actually what we saw is all this is correlated. So when we see that there is no matter falling in, there are no dips coming in, so there is no disk crossing in our way, and there is no infrared emission. And we have seen this kind of pattern repeating, seems to repeat every 2 or 4 years. This means that actually, in addition to the big disk that is as big as a solar system and the small disk that is very tiny, there is something in between that is orbiting the star with a period of 2 or 4 years. We can't see it, it may be a big planet or something that is causing perturbations, but we can see the effect and we can learn that it is there because we see that there is something perturbing this disk and about that period. And as you can see, 2 or 4 years, that's something that you can easily observe. So then this is another object. So CCMA is in the Canis Majoris constellation, and it's called Northwest because there is another one that is Southeast. So it's a binary star, but they're kind of far away, right? So each one of these binaries has its own disk, and actually each one of them is variable in its own way. So the Northwest is the one that I have been looking at. So it's a star that is more massive than the Sun, and it happens to it also the same thing that I was showing you in the initial movie. It has a disk, and from time to time, bigger bits of the disk are falling on the star, and the star becomes very luminous. So then the interesting thing is that when the star becomes very luminous, it also heats up the surrounding disk. And this is a bit like if we were using a magnifying glass. It's a bit strange, you know, because it's not really, we are not seeing things that are smaller, we're seeing things that are bigger, but they get hotter. No, but it's like a kind of a stellar magnifying glass. Normally we will not see the disk in this case because it's too cold. But when the disk gets very hot, it starts emitting in the infrared, and then it even starts emitting in the optical, and then we can see it. So how do we know that what we see is a disk? So again, we use spectra and we observe over time. So if you have a disk, this is my cartoon of a disk, a rotating disk. So you are going to see that part of the disk is coming to you, and part of the disk is going away, and the part in the middle is kind of moving across, right? So then the part that is coming to you is going to produce some line that is going to be shifted to the blue. The part that is moving away is going to produce a light that is shifted to the red. And then we also know from how planets or things rotate around stars, like Keplerian rotation, the things that are very close, they rotate very fast, right? They are also smaller, but these are going to be producing small emissions, so not too big, but moving really fast. So this is going to appear very far from the line center. And then the things that are over here, they are much bigger, so they produce a bigger emission, but it's going to be shifted less. So we can actually tell how big the things are from the emission that we see. So this is just a cartoon of what things will look like if we have a disk, and this is what we observe. So it looks like this double peak from the disk. We can measure how far it will be, so that will be about half astronomical unit, and these two peaks are coming from regions that are between 1 and 3 astronomical units. And okay, it looks like a disk, but you can say, yeah, but it doesn't really, it's not so symmetric. But then actually, because it's not so symmetric, we can also tell how big is each region. So it's actually a disk, but it's not fully flat, symmetric, nice disk. It's probably a bit off-center and has brighter spots than others. One way how you can get a disk not to be nice and symmetric will be similar to what you saw in the picture from ALMA, if you have planets or things forming in there. And then you can see this thing becoming really bright and visible when the object goes in outburst, and then when the object has already accreted all the mass that was falling on it, it goes quiescent and this emission disappears. And this object has also data from the American American Association of Variable Star Observers, also for 70 years or so. So you can actually see this has happened already a few times. You don't have data you see only the photometry, so we don't know what happened to the disk. But if we keep observing, we may see. And now I come to Armon, or the Hubble Variable Nebula. So this image that you are seeing here is similar to the ones from 100 years ago, but these are more modern. They are taken by John Lightfoot from the University of Edinburgh. So they look better quality, but you can see there are still things happening in here, right? So what you can see is there are the shadows that are developing and moving up, right? You can see it looks like a smoking, no? It's much easier to see it here in the modern images than in the old ones, no? And you can also see this is going year over year, in summer it's not visible, and then it comes back, right? So you can see how these shadows are moving. And then I have two of my students that have been working on this object as well. So Chris Templeman was looking at this object with data from the TESS satellite, and what he found is, so from the TESS satellite we are looking mostly at the star, right? So forget about the nebula. We are looking at the object. And then if we are looking at the object, anything that we see changing is not going to be what is reflected in the nebula, because reflected in the nebula is something that is going to be like 90 degrees from us. It's projecting a shadow in the nebula but not coming in our way. So what we are seeing in this direction is something that is coming in front of us. And what you see here is, it's a phase-folded light curve. So we found that the object has a period of about 2 days. So this kind of, it has brightness changes that come back and forth every 2 days. And if you repeat the interval of 2 days and folding it every 2 days, you fold it on top, you see like a pattern. No, it has this kind of M shape. So this is similar to the object I showed you before. We have 2 spots or 2 blobs are coming our way. One is big, produces a big dip. One is small, produces a small dip. And then this is how we get like an M shape. And you can see also the M is not perfect. So from time to time, and this is just 2 days intervals, things are changing. Well, because this is a very small disk that is also changing very quickly. But we can actually see this behavior. My other student, Ruhi Kahar, she started her PhD now, and she's looking at the spectra. And she's also looking at the spectra on the star and on the nebula, and finding a lot of lines, like for instance, these oxygen and sulfur lines, they are forming the nebula when winds from the star are hitting the nebula. And we can also see that this is changing. And if we look at the hydrogen emission, that also is telling us how the material is coming and falling onto the star. So now we have 2 things. We know that there is something crossing in front of us because we see this variation. We see that there is something crossing between the star and the nebula because we see all the shadows and we see all the lines. So what is that? And then I made another sort of cartoon here. So that one didn't come so good. I was making it this morning. I need to improve it. So what you see the nebula here is actually the edge of a cavity. So you have dark things that you can't see because they're dark, but they're like on the sides of the star, right? So these are the 2 dark things. And then what we know that we have in there is we have something that comes crossing in our way and something that comes crossing in the ways from the nebula. So again, we have an object. If we were able to remove the 2 big darkening things, so we are observing from here, we will see that this object has also 2 disks with high inclination. We have one that is coming in our way, we have another one that is projecting shadows in the nebula. The nebula has a bit of irregularities, so when this disk comes in, we get shadows and move there and evolve. And then we know that the period of this disk is about 2 days. So we can just tell that this is very, very, very close. It's a couple of stellar radii, while the period here is a year and a half. So this is more like Earth distance. And this is also a very big surprise, because if you remember the cartoon I was showing you initially, we assume we have a nice blob of cloud that starts collapsing. It forms an envelope that is nice and round, and a nice disk in there, right? And now what we are finding is that many of these objects don't have just a single flat, nice disk. They seem to have different disks, or high inclination disks, or disks that are totally distorted. And we don't really know how this comes. Our solar system came from a very flat disk. This is why all the planets are in the same plane. So, but we have also seen other systems where planets are a high inclination. It could come because maybe the systems are binaries and they interact and they pull each other's disks. So actually the disk of GW Ori, which is a triple system, is a very horrible thing with many gaps and different structures. It's not so disky. And it could be also, if you have other objects like CCMA, it's a binary, they are far, but again, they could be also perturbing each other, or if you have stars forming in a cluster, they could also be perturbing each other. There are also people that say that actually when the material is coming by, it could be also depending on the magnetic fields that you have, to end up with disks in different inclinations. So we don't know, but it looks like having funny sort of disks is more frequent than what we thought. And this is also very nice because it's really interesting to be able to observe them. And I'm just finishing now. So people tend to think that the nice pictures come from when you get a nice picture and you see the sky and the nebula, and it's also cool. But actually the time-resolved data also produces nice pictures, and I'm showing you here other nice pictures. This is one of the pictures I use for trying to find the period of a star. This is for J1604. It's what is called a wavelet analysis. It looks very cute. And this thing here, that is also very nice, is actually the scans from the Gaia mission that is measuring the distance of the stars by making essentially super thin scans over the sky, repeated them over and over again to be able to measure the position of every star with respect to every other object. And that's a way it's mapping the sky. So time can give you details of things that are too small to getting an image. And the other important thing is that actually we are gathering a big amount of good observations that is now long enough to study the formation of planets like the Earth and the evolution of the disks at these kind of scales. And this is only getting better, right? Because we keep accumulating very good data. And we can get a lot of details even if our telescopes are not so large, which actually brings me to my last point. There are a lot of efforts that are being done by actually citizen scientists and amateur astronomers. So the HOIS project from the University of Kent, that is a colleague of mine who is leading that project, and they're using the small telescope that they have in Kent, but they are also getting observations from other people who can contribute to look at young objects. The American Association of Variable Star Observers has incredible data for more than 100 years for some of the objects. And then actually some of the data that I have been using for looking at the long timescale evolution of these variable objects comes from amateur data as well. And there are also, analyzing these huge pools of data is also something that is kind of hard. So there are also many projects that are working on including amateur astronomers and citizen scientists analyzing variable data, like for instance the SSN or All Sky Automated Survey for supernovae is also getting people to help with their data. And this object that I show you in the two pictures, the one that is sometimes very red and sometimes is very blue, is actually coming from this survey. So if you want to really go to the very, very tiny detail of how stars are forming, you can't just wait for a big telescope to happen, because even if you have several kilometers, it's not enough, right? So what you need to do is do other things, and actually color and time are really wonderful tools to get more information about stars. So thank you very much, and if you have any questions, let me know.
Give me the lights.
Sing for them. Aurora, thank you so much. That was just a fantastic talk. Comments and questions for Aurora?
I've got a comment and a question. The comment is the thing about disks around stars. That is quite a revelation. I never even thought that that could happen, that a star could have one disk that way and another disk that way. You know, it's amazing, and it comes to all sorts of ideas as to how they could have formed. I think you mentioned a few of them, and what came into my mind when I first saw that, I thought maybe the stars were all close together in a globular cluster, and they had close interactions, and material was pulled off, and then another star came in another direction, and all that kind of thing. It's just a comment. But that
this one of the ways that you could form a star with this with different inclinations will be interacting with other objects.
Yeah.
Or also moving to the cloud and maybe like gathering material in different directions.
Yeah,
but we don't really know.
No, it's all the angular momentum. No, it's very strange. The other thing, there is a question. There was a slide earlier on that I was fascinated by that, and it was the one where you had the size of object against time.
Yeah.
And different instruments of observation, and they were all parallel, apart from the Kepler. The Kepler one was slightly inclined And I thought, that's strange.
So I'm trying to go to the slides, but it's getting stuck with the movies.
It's the one that it was a Kepler instrument that was different from all the other ones, and I thought, why was that? Something to do with relativistic effects, maybe, I don't know.
The Keplerian rotation was different. Okay, so I had there. So what we have. So the Keplerian rotation is different because it's not a constant velocity moving through space. No, like light.
Yeah.
It's just moving at a constant velocity, or if you have a sound wave, it will also have a velocity and it moves constant.
Yeah.
But if you have Keplerian rotation, it depends on the distance. So it's not like a constant velocity moving through space, but an object that is close to the star is going to rotate faster, and an object that is farther out is going to rotate slower, and it's not the same kind of relation.
Right. Okay.
So that's the reason.
Actually, a follow-on from Graham's question. If you can get these stars with perpendicular dust clouds, does that mean you could potentially have planetary systems that are perpendicular?
Yeah, and actually
And we've never spotted them. Is it just because our technology and techniques are
They have-
still different?
they have spotted some planets that are very odd inclination. So we can actually detect how the planet is rotating versus the star. And there are planets that are actually kind of crossing the star in a different way. So if the star and the disk are forming from the same cloud, they should be rotating in the same way, like in the solar system. So the planets rotate like that, and the sun is also rotating in the same way. So we may not have seen planets that are at different inclinations, but we have definitely seen stars where the planet is rotating like perpendicular to the stars. So in that case, we have formed the star and the planet from the disks that have different inclinations.
Yeah, the only cases I've seen of those, they speculated that those have been trapped objects. So it got too close to the star and it's been captured rather than being formed that way. But
Now
you'd
we are
expect to see
finding
more of
also,
them.
we are finding more, and then also there was this issue of objects that have dips, like what they are called dippers, or they are also called Uxor variables, right? So in general, people say, yeah, this is something from the disk coming in. But then you see, like, I don't know, 40% of the stars are Uxor variables. So you can't have 40% of these very thin disks just seeing edge on. It doesn't make sense. So we are finding that there are a lot of systems that have really material that is not just flat in a disk, but kind of at high inclination. We don't know yet how many. So this is also one of the things that I want to explore with my 5-year project with the 80 centimeter telescope. Try to see statistically, look at the cluster, see over 5 years, how many of these objects are deeper, and how many of them do you expect to have the disk really edge on versus not.
That would be interesting.
Yep.
On one of your slides, you were showing the 24 micrometer from the Spitzer, and it looked like it was out of focus, and I was wondering if that was like, if it was low resolution and it's sort of been brought up and sort of generalized. And you also mentioned, I think, diffraction patterns or something, and I'm just kind of curious how you can tell when it's a diffraction pattern versus gaps from planets, like what you showed.
So well, the diffraction depends on the wavelength and the aperture of the telescope, right? So then normally you can characterize very well what kind of diffraction pattern you're going to see. So it's something that is called also the point spread function. So this is how a point source will look on your telescope.
Okay.
So this is something that people already, even before launching, they're measuring it in the lab. So at Spitzer, because it's 70 centimeters, 24 microns is already very long. So then diffraction effects are very huge. Like, for instance, if you have a look at the other image that I had, 4 microns, you don't see that so much because it's much shorter, but 24 microns or even 70 microns, the diffraction is much bigger. But this is something that is very well characterized, and actually you use it also to know whether things are extended or not, because this diffraction pattern appears when the source is a perfect point source. So if a source is a bit extended, the diffraction pattern disappears. So it may look like only like a dot or like a few pixels, but if you see these kind of rings, then you are sure that it's smaller than your resolution. And if you don't see them, then you know that it's a bit bigger.
Okay.
Do you think it's possible that there may have been slightly off-centre or an alternate disk in our solar system when it was formed, and there might be an object or two maybe way out in the Kuiper belt that's orbiting in the...
Yeah, so there are objects that are weird, like there is this object that is called Sedna.
Oh yeah.
That has a very, and that one has an odd kind of orbit. It has a very elongated orbit, and it has also some angle. So one of the ways that we could have formed Sedna is actually interacting with another star, pulling it there. These disks that we see that are inclined, they tend to be much closer in. So all these things are, it may be also a selection effect, because we are looking at them when they cross in front of the star. We are looking for variations that take days to years. So then if there was something much farther out, we need to
much
we need a couple of 100 years. So it could be also a selection effect that we are seeing a lot of inclined things in the inside. Could be also that it's maybe easier to kick things out of the plane in the inside.
Yeah.
But yeah, we also see some objects. Yeah, like in our solar system, Sedna is out. Pluto is also crossing the way, right? So we have things that may have been perturbed and assigned in odd ways.
This thing could also relate to the mystery as to why the sun's equator does not coincide with the plane of the planet. Because the sun is tilted, you see. It's strange, the way that you tend to have a train of thought on angular momentum when things collapse. Eventually angular momentum starts in a disk will form, and that the angular momentum of the disk tends to be in the same orientation as the central object. But of course the sun is tilted at 27 degrees.
Yeah, it's not a huge amount, but it's
That's significant.
but this is also something that we see. We have also in the pictures that I saw in the cartoons, I usually put this kind of lines. These are the magnetic field of the star, which is usually how the matter from the disk is falling or is following the magnetic channels. And what we are also seeing is that these magnetic fields, initially people thought it's like a dipole. So you have the star is rotating like that, it's like that. But we are actually seeing a lot of inclined dipoles.
Planet Uranus is a good example.
Yeah, but we also see these in other objects, in stars, that they seem to be inclined as well.
Interesting.
Gosh. Any more questions or comments for Aurora? Well, I can only thank you ever so much for coming, and absolutely wish you the best for your 5-year project and also for your other lab work as well, because fascinating work. Come back and tell us what happens next.
Yeah, actually, if I get some interesting results, I'll be coming. Yep. Hopefully that will not take the entire 5 years, because we'll be observing and analysing all the time.
Come back anytime then. Thank you so much.
Thank you so much.